Good morning, everyone. Please look at the screen that we are having. Well, this is our plan for the rest of the semester. Okay. And we mentioned this yesterday. And please, so your exam time, you don't have the whole weekend. You only have 3 days. Okay, Wednesday, Thursday, Friday. And we do it online. So there will be no classes on Wednesday and Thursday. All right. So do you have any questions? You will have a last quiz this week. And that will be counted for extra credit. Okay, so yesterday we covered mathematical induction, and get your question ready, please. We will do review tomorrow. We'll do review tomorrow, and we have covered much of these materials. Of course, a lot we haven't got time to do. Any questions? Okay. If you don't have questions, we're gonna work on parametric today. Okay, you should find these topics in the notes titled Parametric 1. Let's see which page could I find this. Parametric. In the section of parametric, wait, I think this is passed. No, this has passed. Parametric. Oh, I made some changes to this, to a lot of the stuff in the beginning. Let's see, parametric should be right after trig. There. In the notes, it's on page 122. Okay, parametric. Parametric 1, page number 122. Okay. All right. So we have 3 tasks. Okay, 3 tasks. Find the rectangular coordinate equation and sketch the curve, indicate the direction. Okay, we actually would start with B and C to talk about the ideas, Okay, so first, so we start with the B. Okay, so what is parametric? What is parametric? Right? Parametric equation. Well, we start with a rectangular system. Right? Suppose we started a rectangular system, and this is the rectangular system we are very familiar with. Okay, let me make it 150% and make some adjustment to the scale. Okay, so this is rectangular system. In this rectangular system, what do we used to do? Say if we plot a point, right? All the points, for example, a point, right? A point, say 2, 3, right? this pair we call ordered pair will have a spot. In the rectangular system. Okay, it's a dot. And the dot is marked as 1, 2. I'm sorry, 2, 3. 2, 3. Right? And the quantity, okay, you see the x coordinate, which indicate the horizontal distance to y-axis, and the 3 indicate the vertical distance from the point to the x-axis. And these are numbers. These are actual numbers. Okay. But in rectangular system, what happened is that these 2 and 3, they will be dependent on another variable. Typically, if you imagine in our real world, if you talk about fourth dimension, that typically will be t, time. So depending on time or t doesn't have to represent time, but in a lot of physics situation, it's representing time. So these numbers 2 or 3 is going to be dependent on time. So these are no longer a single number. It's going to be an expression. Okay, so in excuse me, suppose that we have a point in, excuse me, I think I need to go get some water later. Okay, so the x coordinate depends on a time, which is a function of time, and the y coordinate is a function of time, or a third variable t. Okay, so it's no longer just a constant. It's to depend on the time. Excuse me. So depending on the time, the point could be different. Okay, so let's see how this works. Okay, and then we're going to look at the trajectory of all these different points at different times. Okay, so this is parametric, and the t is called parameters. Okay, so t is called parameters. It's called a parameter. All right, so that word t, right, both x coordinate, y coordinate depends on another parameter. This is parameter. So that's why it is called parametric. Okay, let's see how it works. Okay, now let me clear all of these. Okay, so x as a coordinate it depends on another parameter t, and y depends on another parameter t. This is the typical way we write it. Okay, and let's look at the example. The first example I'd like to take you guys to see would be the first one. Let's look at the first one. Okay, it's simple enough, right? The first one. And I'm going to still using this rectangular system. I'm going to use this rectangular system. I'm going to remove that point. Okay, so it's a blank. It's a blank. And in this particular system, you can see in the definition, excuse me. In the definition, you will see, okay, x is a function of t, half of t. Okay, y is a function which is dependent on t. Then you say, what is t? What is t? Well, t in this case, there's no restriction. There's no restriction. So there's a natural way we can say, oh, okay, t can be any real number, because you can just look at this. The relationship between x and t can be any real number. The relationship between y and t can be any real number. Therefore, so this is an individual relation, this is a function, and this is another function. And then these two functions together, we determine the value of x and y. And x, y will be plotted on this, on the system. Okay, so let's get started. Okay, let's get started. So we're gonna set up a system. Okay, so let me give it a couple columns. Okay, make sure we have enough time and space, right? And typically we will plot x, right? And we will plot y. But both x and y are dependent on t, okay? So when our ordered pair is going to be established only after t, the value of t is determined, okay? Because t can be any real number, so we can choose any real number, right? So I'm going to choose, say, t equals to, consider the easiness of calculation. I'm going to choose, say, t equals to -1. If t equals -1, let me choose t equals -2, right? Because I don't want to deal with fraction. So then x will be equals to 1/2 of t, and t now is -2. And that equals to, that product equals to -1. And y, which is t minus 3, right? And when t equals to -2, -2 minus 3, that's -5. So we got a point, and this point is -1, comma, -5. So that's parametric. That's parametric. Do you guys see that? Okay. So now I can plot this point -1, -5 at a time t, -2. So I'm going to put that in the chart. Put that in the chart. Let me make it a red dot, right? So make it easier to see. There's a dot. Okay. So you guys got the hang of it, right? So I'm going to give you a couple more points, and you're going to plot them. And I'm just going to get a little bit of water for myself to drink. Okay, so I'm going to give you point t equals 0, point equal t equals to 2, equals to 4. Okay, so what you do is that you're going to follow these steps. Okay, you're going to plot 3 other points on the graph. You got it? You guys got it? What to do? Okay, I'm just going to get a little bit of water to drink. Okay, I'm going to get some tea. Okay, I'll be right back. All right. The same function for x in the relationship with t, and the same function for y. Okay, so all we have to do just plug in the numbers and then compose our points. Compose our points. Okay, so for 0, that's 0. For 0, and that's -3. So we got 0, comma, -3. For 2, and that's 1, -1. So 1, comma, -1. So 4, and this is 4. So that's 2, and that's 1. So 2, comma 1. Okay. And obviously this process could continue, right? It could continue, right? To do more. So I'm going to give you maybe just one more. Okay, just let's do 6, and this is going to be x is going to be equals to half. It's pretty easy, right? It's pretty easy. The idea is pretty straightforward. And y equals to 6 minus 3 equals to 3. So here we got the point 3, comma 3. Right? Yep. Okay. So we're gonna plot points after points. Dot. Okay. Another one. 1, -1. Red dot. Red dot. And 2, comma 1. And one more, 3, comma 3. You can see we can plot the points forever. We can plot the points forever, right? And then we're going to connect the dots. Okay, we're going to connect the dots. It looks like all these points are on the same line. How, if I connect these dots, as what we see here is that as t increases, right? So we chosen the point that we chosen the value that t goes from smaller to larger, and the point is going in a certain direction. Okay, there's a certain direction that the point goes to. So parametric has a sense of direction, which when we draw lines, we didn't have. Right? There's a sense of direction. As t goes high, as t getting larger, the point is going in a certain direction. It doesn't always go up, certainly. It could sometimes go down. It could turn. It certainly could turn, right? Because imagine x and y as a function in relationship with t. These relationships can be any relationship. Could be sine, could be cosine, as we see in the examples. Okay, all right, you get it? So now the question is, if I want to find out, because we know that on this plane, there is a line equation that we can discover, right? We can draw this line to connecting all of these dots. And what will be the line, or what will be that line? Well, parametric equations sometimes can be transformed into the equations that we are familiar with. I say sometimes, because some other times it may not be as easy. It may not be as easy. Okay, so I want to show you something here. So how do we combine these two? How do we combine these two? I'm sorry. Okay, and get rid of t. Get rid of t to see what do we get. Can we get that? The answer is yes, in this case, right? Because from the first equation, if we do it algebraically, and we get t equals 2 times x. So t equals 2 times x, right? And we plug in the t equals 2 times x. In the second equation, t is replaced by 2x. And we got a line equation. If we graph this line equation, we will connect all these dots. 2x minus 3. Boom. Connect all the dots. So the parametric and the rectangular has some relationship. Sometimes they can transform. Okay. There's something that the rectangular, well, the xy equation has. And there's something that parametric has, but the xy equation does not have, which is the sense of direction. The sense of direction, right? Because when we work the parametric, we know the direction. There's a direction as t increases. There's a direction. But if we simply graph y equals 2x minus 3, we're not going to see that direction. Okay, we're not going to see that direction. That's the difference between parametric and the rectangular equations we are familiar with. Okay, so by now we have done all 3 tasks, A, B, C. Okay, the first one is eliminating the parameter t and sketch the curve, and we got a line and indicate the direction of movement as t increases. So that's the direction of movement as t increases. So we have done all 3. We've done all 3. So did you get it? And this is a so-called parametric. This is a so-called parametric. Got it? Do you want to try one? Do you want to try one? I'm going to choose one for you. Ready? All right, so let's do something more interesting. Okay. How about we try number 9? We try number 9. You guys can practice as much as you can. I give you lots of exercise there. And each one can be done in similar ways. Each one can be done in similar ways. Okay. So I would like you guys to try number 9. Let me see if I can put an arrow. I can put an arrow using this software. Okay. Do I have an arrow? I doubt it. I think the labeling doesn't. I just have to do that arrow physically using the annotation here. Okay, so you guys know the arrow, right? So write this down. So this is the arrow. Okay, this is the when you work these questions, you're gonna put these arrows that way. Okay, but sometimes you may need to put multiple arrows. Okay, we're gonna look at this one. We're gonna look at number 9. We're gonna look at number 9. Okay, so see what kind of situation is number 9. Number 9, we have two rows. Excuse me. Oh. Number 9, x of t. I want to use these notations so you get familiar with it. Okay, e to the power t. So this is like the function notation, isn't it? Function notation. E to the power 2t. Okay, we still use the same rectangular system. All right, so delete that point that we had, for example. Okay. It seems that I use this graph quite a bit, so I'm going to use this, just put this, I'm going to save it there. All right, so we're going to plot the points, okay? And we have established a table, so we can just use this table. Okay, clean up, of course. Okay, so this is e to the power t, and this is e to the power 2t. 2t, right? And I'm going to choose some t values. Right? I'm going to choose some t values. But one thing is certain, before we plot the point, we can do some analysis, can't we? We can think of the domain for t, right? What's the domain? Obviously, these are exponential functions. T can be any real number. But what's more interesting is that we know e to the power anything is always a positive. So this is always a positive. And this guy is always positive. So our points will not be in the other quadrant, but only in the first quadrant. Do you guys see that? Just because your x coordinates and y coordinates will always be positive for any t. Okay? Therefore, you will make some adjustment to your rectangular system. So for example, I'm going to make it just show me the first quadrant, because you're not going to get any points outside the first quadrant, right? You're not going to get any points outside the first quadrant. And you're not going to have 0, 0. You're not going to have this point. Because you will never be 0, right? So you can have some idea about where you're going to get the points in this case. Okay, so we're going to work on our points. We're going to work out our points. There's a chat message. I'm sorry, I missed it. Can you go over in depth about the exam? Is it time sensitive? It is time sensitive. There's 3 attempts. Okay. I'll put the chat right here, so I won't miss it. Okay. So let's do the points. Okay, this time to be easy, I'm going to make it -1. Okay, so 0, 1, 2, 3. Okay, so let's do the points. X will be equals to e to the power of -1, right? And y would be equals to e to the power of what? T equals -1. So this is going to be -2, right? So 175%. 175%. All right. Okay, so you basically have 1 over e, 1 over e squared. These numbers should not look very strange to us, right? We've seen them before, haven't we? Have we seen them before? Yeah, it shouldn't look familiar. It shouldn't look strange to you. 0. Excuse me. e to the power 0. What is e to the power 0? Equals to 1. 2 times 0 equals to 1 as well. So we have a point 1, 1. Okay. And the next point is e to the power 1, e to the power 2. So that's e squared. Okay, you guys we should mark the points. You want to mark the points. Like the previous picture, actually, I didn't mark it, but please mark these points. Hold on, let's go back a little bit. Okay, I should do the example myself because I require you guys to do it. Okay, you need to mark the points for me. Okay, the first point is -1, -5. I want to give you the complete answer. It's 0, -3. That point is 1, -1. 1, -1. Okay. And this point is 2, 1. 2, 1. And that point, 3, 3. I'm sorry, I meant to mark it. You need to, when you present the answer to your teacher, whoever, you need to mark these points, you plot it, and you also need to add the arrow. Do you guys follow me? Add these arrows to your work. And that would be called a complete work. If you don't have the points labeled, you don't get that point for those points. You don't get the credit for those. Okay. So this will be a perfect piece of work. You mark all the points, you label all the points you have. Right. When your teacher asks you to mark your points, that's what it marks the point. If you just plot the point, you don't tell the reader what the numbers of the numbers that are associated with the points. It's incomplete. Got it? Then you say, well, they can see the coordinates. Well, couldn't you tell the reader the most obvious? Provided you want to get the points from your professors, okay? If you don't want to get the points from your professor, don't do it. Don't do anything, okay? To let your professor figure out if you know how to figure out, if he can figure out about you, okay? Because the whole point is your professor is assessing you. Your professor is assessing you, so you want to tell him or her what you know, okay? So sometimes you pointed out the most obvious. So that's the answer, okay? That's the answer. For me, I'm working between two softwares, right? I can use the software to mark the point, but that's going to take a long time. So I'm doing it this way. So I want you guys to write it down before I move forward. I apologize for this change of in the middle of the other question. Did you write it down? So you know what is the answer? How the answer look like? Okay, so now I'm going to clean this up and move forward right here. Okay, and then for these 2 points, for these 2 other points, okay, so this is square, square, and this is 2 times 2. And so the next point is e squared and e to the power 4. Okay, and I think I'm not going to do the third one. Okay, oops. And you don't have to do the third one because the numbers get too big. The number gets too big. Okay, I will have to make some adjustment to the chart. But anyway, we just do 4 points in this case. 4 point in each case. And then I'm going to mark these points one by one on the graph with arrows. Okay, so plot points. And this is 1 point, a red dot. Second one, 1, 1, e, comma, e squared. E squared, e to the power 4. Okay, for which I will have to make some adjustment, e to the power. Wow, it's a very large number. But anyway, I'm going to say 20, and this is 90 to accommodate all these points. To accommodate all these points. It looks like these are getting too close, right? It seems that they're at 0. That's not true. That's not true. We know the point. None of the points are going to touch the 0. So I'm going to make it smaller. I'm going to make it smaller. Okay. That still should be above it. So 8. All right. So it's off. It's off. So what we're going to do is that to mark those points, the first point we're going to mark is going to be what? 1 over e and 1 over e squared. Okay, you mark those points. The second point is 1, 1. And you also need to put an arrow there. Okay, and that point, the third point, is e, comma, e squared. Okay, I'm not marking this point because it's going to be off the chart and make the picture looks a little awkward. Another arrow. Another arrow. Okay, so now if we connect the dots, what are we going to see? That's the question. If we connect the dots, what are we going to see? Right? This curve will never touch x-axis and it will never touch the y-axis, right? Because x, y always positive. So the curve probably starts somewhere very, very close to 0, very, very close to this dot. Okay, as say t equals to -infinity or something, right? Negative infinity doesn't exist, but it just say -10,000. So the point is very, very close to the origin, but never touched it, right? So that's a curve. But we're only getting a sketch. We're only getting a sketch, right? So when we graph this, we like to know the rectangular form, just getting rid of the t. Can we get rid of the t? Did you guys mark the points? Okay, mark the points. Let's see how we're gonna get the rectangular form. How do we get the rectangular form? You just have to use a little bit of algebra. We just have to use a little bit of algebra, okay? So you can see e to the power t is x, right? So e to the power t is x, and y is e to the power t, right? And e to the power 2t is e to the power t squared, right? So that's just going to be x squared. So the curve we know we get here is actually x squared. But knowing where it comes from, okay, so this curve is not the curve we know. It's x is larger than 0. Right? Because x is always larger than 0. Y is always larger than 0. So when we graph this function, when we finally graph this function, of course we know this function. This function is just x squared. Who doesn't know x squared, right? And we connect the dots. But this dots, this specific curve we're drawing will never touch the origin. So on the origin, I'm going to put a circle. You see that? So this is a parabola. Half of the parabola. It doesn't touch 0, 0. And this will be the curve. And then to complete the graph, right? You're going to put arrow, arrow. Okay. Maybe like that. Maybe just make the arrow just a little bit larger, a little smaller. Okay, is that better? That's fine. Yeah, just this way. And also mark the points. Okay, I just mark the points. I have given you the examples of marking the points. Just mark all the points. In this case, you just have to mark 3 points. E squared. Got it? And that will be the complete answer. We're done. Make sense? Okay, so we did one straight line and we did exponential. And let's do trig function. Let's do trig. Okay, let's see what trig function gave us. What kind of picture does trig function give us? Okay, and this will be, I will make this opportunity for you to review trigonometry. Domain and range, etc. Right? Domain and range, etc. Okay, so I'm going to choose a question for you. I'm going to choose number 12. Okay, we're going to do number 12 and number 13, and let's see what's the difference. Okay, number 12. Right? So we have that function here. But this time, it's a sine of t, cosine of t. We no longer have that greater than 0 or not. But sine has its range, while cosine has its range, right? What's the range of sine? What's the range of cosine? Do we know that? Do we know that?
From -1 to 1.
I'm sorry?
From -1 to 1.
Perfect. That's it. That's right. We need to be aware of that, right? We need to be aware of that. So I'm going to put that information, right? -1 less than equals to sine of t less than equals to 1. And cosine is the same. So when we set up our rectangular system, we know that the x value will always be between -1 and 1. Y value is always between -1 and 1. So when we set up this system, and in terms of view, you're just gonna choose between -1 and 1 and -1 and +1. Does that make sense? Yeah, does that make sense? Because you're not gonna be outside of it. Okay, you're not gonna be outside of it. And that's plus and points. That's plus and points. So I'm gonna make a number of rows, a number of columns. That should be enough. Oops. I'll put it on this side. Okay, so I'm going to give you some values of t, and you're going to do the calculation. You ready? So sine of t and y of t equals to cosine t. And our points will be x of t y of t. Okay. And now, what are the t's I'm going to give you? I'm going to give you some t's. Okay. I'm going to give you some t's. But knowing that t serves as angles, so I'm going to give you some radians. I will give you pi over 6. Pi over 4. Pi over 3. Pi over 2. Whoops, sorry. And 2 pi over 3. Three pi over 4. Insert row. 5 pi over 6. So far, just this many points. Did you get a hang of it? Oops. I'm just going to reduce this, simplify. So pi over 6. Isn't that interesting? Isn't that interesting, the way we get our points? We make sure T increases, right? So we keep going, we can see the point is going around the unit circle, going that way, and keep going. Okay, it keeps going. So it's a sense of direction, sense of direction. Parametric. Okay, so that's parametric. Sorry. So let's complete all of these. It takes some work, right? Oops. Right? Did you get it? Be patient. You get all the points, right? Be patient. We get all the points. And we also discover the direction, right? Okay. So we just did half of it, right? Just did half of it. So it goes in this direction, right? So you're gonna put the arrows. We're gonna put the arrows this way, that way, and mark the points. Mark the points. Okay, so let's mark the points. The first one is half, and then √3 divided by 2. And the next point, √2 over 2, √2 over 2. And that point is √3 over 2 half. And that point, 1, 0. And this point, 0, -1. Okay, so you mark all the points you have plotted. You mark all the points we have plotted. I cannot move right now because all these, if I move, everything is messed up, right? Messed up. So you just mark the point. It looks like we're getting a circle, right? Because you see these two pairs, these two numbers, right? They're on the unit circle. They're on the unit circle, right? Half squared plus √3 over 2 squared equals to 1. So the square of each is there equals to 1. So we anticipate we're getting a circle, and how the circle is formulated, the circle is formulated clockwise, not a counterclockwise. You see, clockwise. You follow me? So that direction is a clockwise. So I'm waiting for you guys to write it down, and then I'm gonna move to the how do we get rid of the t? How do we get rid of the t? Did you write it down? How do we get rid of the t? Okay, this is how we get rid of the t. X squared plus y squared is equals to sine squared of t plus cosine squared of t. And that equals to 1. So we have a unit circle. We have a unit circle. We have a unit circle. Okay, that's the unit circle. right? So let's draw the unit circle on the graph. So that's a unit circle. Okay, connect all the dots. And then to complete our job, right, we already marked the points. You just have to put these arrows in place. Clockwise. You keep going, you're gonna get the other pass, the other half. Okay, got it? And with the marked points, with the marked points. Okay. All right. So we've answered all three questions. That's essentially parametric. That's essentially parametric. Okay. In your calculus class, you're gonna learn how to, do other tricks with parametric. Okay. And next, we're talking about, we're gonna do number 13, right? Let's look at the difference. What's the difference? What's the difference? Number 13. Number 13, the only thing that changed is t is doubled. And of course, this is still true, right? It is still true. The range about it is still true. Still, the range about it is still true. Okay. Now the question is, what's the difference, right? Because if you use the same trick, you're gonna get the same circle. You're gonna get a unit circle again. You're gonna get it. You're gonna get a unit circle again. It is still unit circle. But this unit circle and the next unit circle, what's the difference? In the consideration of the parameter t, right? If t is a time, what difference it makes, right? What difference it makes? Okay, so I'm going to show you that difference. Okay, to show you that difference, I'm gonna create this table. I'm gonna show you how I create this table. Okay, now it's 2t. Okay, it's 2t. Okay, and the points I'm gonna choose.
Professor, you gotta switch cosine and sine.
Oh, sure. Oh, yeah, thank you. Cosine. This is a cosine, right?
Yeah.
And this is sine. Okay, there's still unit circle, right? Unit circle. And this is a cosine and this is sine. Okay, there's some tweak, there's some changes. There's some tweak and changes. Okay, so ignore all of these. Oops. I don't mean to confuse you. So when I'm choosing my point, okay, I'm going to choose half of it. I'm going to choose half of it. Then you may ask, why do I choose half of it? Why don't I just choose just arbitrary any real number? Because these are special angles, right? Everything, all the points are halved. Okay. We know we're getting a unit circle, right? We know we're getting a unit circle. If you compare with this question, number 13, I think number 13, number 11 would be a better comparison, right? But we chose number 12, but that's okay. They're both unit circle. They're both unit circle, okay? What you're gonna see is that this, if you have a particle on the unit circle of number 12 versus it's on the unit circle of number 13, the particle that's running on the trajectory of number 13 is going to move faster than the other one. That's what I want you to see. Okay, you can see I have half the time I reach the same point. Okay, half the time reach the same point. You guys follow me? Do you get what I'm saying? Okay, suppose I do. Okay, so let's do this. I think I'm going to bring up number 12. I'm going to bring up number 12. Okay, for your comparison. In terms of plotting points, right? Because we have already done some plotting points. Okay, so I'm going to bring up number 12. No, number 11, sorry, number 11. Because I really want you to see that. Cosine T, so this is a cosine. Sine T. Right? What did I do here? Sine, sorry. This is sine. I made some mistake somewhere, okay? So I'm going to bring, I should have chosen 11, but it doesn't matter, okay? So suppose, because you guys are already pretty familiar with the points, right? So next, what I'm going to choose, when I choose the points for number 12, we didn't do 12, but now we're going to do 12 and 13 together. How about that, right? We're going to do 12 and 13 together. Make it smaller fonts, right? You see the points I've chosen. This is a cosine, and this is a sine. Sine T, sine T. Okay, so all of these are cosine. Okay, I'm going to put it here, right? That will work, right? Would that work? And of course, the points will have to be adjusted. Oh my God, sorry. The point will have to be adjusted. Right, so these points will be adjusted. Okay. So now what I bring together is number 11 and 12. They're both unit circle. They're both unit circles. Okay, so this is unit circle. It's 1T. And this is the this other one is unit circle. We already know it, right? We already know it. What's the difference? Point-wise, okay, point-wise, on 11, on number 11, the unit circle is a cosine t for x, sine t for y, right? Do you guys follow me? For number 13 is cosine 2t for x and sine 2t for y, right? So the difference is there's this little doubling. There's a doubling effect. What will happen? So I want you to calculate the points to experience that. Okay, so for this point, it's going to be root 3 over 2 comma half. Okay, so we're going to see a couple points to see that. Cosine 2t is 2 times pi over 6. Oh, I'm sorry, half. It's half of that, right? Because 2 times of half of that. And sine 2t, okay, 2t all right, so that point, okay, it's the same point. Do you guys follow me? But it reaches the same point with half the time. Do you guys see that? Because this takes pi over 6, say, seconds, and this takes half of pi over 6 seconds. Do you follow me? That's what I want to explain to you. That's why that if you imagine there's a particle, okay, on this unit circle versus a particle on this unit circle. The particle on this unit circle is going to circulate the unit circle faster than the other one, double the time. So that's a difference. That also shows the difference the parametric can demonstrate to us versus just a rectangular system. Spam. Okay, do you guys see that? That's what I want you to see. And that's how I, make the point. So now I want you guys to actually plot those points. Okay, I think I have a faster way to do this. You guys just take your time, okay? I want to get it done before the end of the class. You gotta get the hang of it. Okay, guys, where are you? I try to finish this. So you're gonna see and truly see it, okay? Truly see it. I remember when I was in college, when the professor talked about this, he didn't elaborate why. I was very confused. So how come he get that? How come he draw that conclusion, right? And after class, when you start to plot the points, you start to see very clearly. Okay, so I hope to give you that kind of insight, and then you understand everything related to it. Okay, you understand everything related to it. Okay. Okay, you can see point wise, right? Point wise on number 11, right? This point. I'm going to make it a red dot. Okay, wait, where's that point? Oh, I didn't add it. Right, so that dot is the same dot. It's really the same dot. Okay, it's really the same dot. So let's plot another dot. Okay, the second dot. And this is the second dot. Right, that's the second dot. Oh, the other one should, well, it doesn't matter, right? Doesn't matter. So these two dots, you can see they go in the same direction. They even go in the same direction. We're talking about 11 and 13, okay? The points plotted here, right? However, to reach the first dot, right? In number 11, it takes pi over 6 amount of time. And in the number 13, it takes half of pi over 6. Do you guys get what I'm saying? So if you imagine the particle, suppose you have like, this is the particle, right? A molecule or atom, right? They're gonna go from this dot to the next dot, right? From this dot to the next dot. Which one would travel faster? The one in number 13 travel faster. And with double the speed. Do you follow me? Because the amount of time, the amount of time it takes a particle to get to that point, to get to the first point, is half the time. You see, it's a half the time. Do you get it? So even though everything, when you graphed it, this is pi over 6, this is a half the time. So the particle that's circling on this number 13 parametric circle versus a number 11, the parametric circle, the particle on number 13 travels twice as fast. And that's the difference. Do you guys follow me? That's the difference between these two parametric equations. Got it? Okay. With that said and done, and here are the points. Did you guys have time to write it down? Okay, I know I was a little too fast in this area, but you can watch it over if you can watch the recording over if you wish. Okay, and to better understand this, the idea and what it leads us to, right? There's another dimension. I don't know, guys. This kind of question often reminded me when my children were younger. We went to Legoland, right? Did you guys go to Legoland? I'm sure you've been to Legoland, right? There's a 4D movie. Do you remember that 4D movie theater? Okay, maybe you want to go there again. What is that, a 4-dimensional? What is that 4th dimension? We know that we're not dealing, in this class, we're not dealing with 3 dimension yet. We're dealing with 2 dimension, right? So suppose we're dealing with 3 dimension. You're gonna have X, Y, Z. And the movie says we're gonna have a 4 dimension, 4D movie. What is a 4D movie? It's a time. The fourth dimension is, in our real life, is more like, at what time, where are you at different time? That's a 4-dimension idea. So even though physically we are a 3-dimensional object, but we at different time, this body, your body, my body, your body is at different location. So that time added another dimension to our living. Does that make sense? So parametric is to describe that process. Okay, for example, the trajectory of planets, right? The trajectory of Mars, the trajectory of Earth, right? We know they go on the ellipse, right? The trajectory is the ellipse. But at different time, where it is on, what is the location on that ellipse? That's what it was trying to describe. So parametric is trying to describe or find patterns of the movement of objects at different time. And the objects could be particles, it could be molecule, it could be atom, it could be you or me. It could be a mouse, okay? It could be a termite. It could be, or cells, right? Cancer cells, for example. So this parametric idea is really, it's at another level of describing the real world. We're closer in terms of the tools to learn about natural phenomena in our studies. Okay, so that's how I see it. So with the remainder of the time, we're going to do one more parametric. Okay, you're going to see ellipse. Okay, I already give you the answer, right? I already give you the answer. So I'm going to take you to number 18, which is the last question. Okay, I wish to give you these tools algebraically. Okay, so number 18. Number 18, you have this guy. Okay, is 4 times sine of t and 3 times cosine of t. Cosine, sorry, cosine. Which cosine of t, okay? All right, now, knowing that sine t and cosine t, their range, right? We know these. That is still true, right? And to make it easier to see, that doesn't matter. Cosine t. Okay, well, how come I couldn't type that correctly? All right, so when we multiply by 4, what will happen? Those will be between -4 and +4. And this will be between -3 and +3. Do you guys see that? So when you set up your rectangular system, you know the range. We know the range. The x direction is going to be from -4 to +4. The y direction is going to be from -3 to +3. Okay, and I already told you this is ellipse. How did I get it? Right? How did I get it? Well, from the first one, okay, from the first one, we got sine of t is equals to x over 4. Right? Divide both sides by 4. So I'm just going to simplify this as x. Okay, from the second one, right? From the second one, and you already know what we're getting, right? From the second one, we're getting cosine t is equals to what? Y over 3. Okay, so that's a y. Okay. And then sine square over cosine square, plus cosine square. So x over 4. Oh, sorry. X over 4 squared plus y over 3. You see that algebraic operation? It's the same as sine squared t plus cosine squared t. And that equals to 1. And this will give us the ellipse. Okay, so x squared over, oops, x squared. I'm sorry, let me make it larger. Okay, so x squared over 16 plus y squared over 9. And that equals 1. And that's the ellipse. That's the ellipse, right? You guys have learned some conics, right? You learned some conics. We don't have time to go over conics that much anymore this semester, but this is the ellipse. This is the ellipse. So we can graph it. So I'm going to graph the ellipse. If you know what, if you want to know more about ellipse, you can just go to the conic section of any textbook with that topic. So you're going to find that, right? So suppose I'm going to graph this. Okay, so 1 minus I know our time is up, so that if you have to go, you can go. Okay, so that's 3, that's 3. 1 minus that. There you go. I think that should do it. That's half of it. And the other half, that's the ellipse. Which direction it goes, right? Which direction it goes, you're going to plot points. We're going to have to plot points. Okay, so what are the points you're going to plot? I'm going to give you this because tomorrow we're going to do the review. And if you have any questions, so let me give you the points that you would like to plot. Okay, so I'm going to give you these points. It's just a bit more calculation. I will modify this to your need. Okay, so I will still be choosing these points, but x is 4 times of sine t, right? 4 times sine t, and y is 3 times cosine t, right? Cosine t. And so all of these will have to be redone. I think it will be, I think we did that in number 12, right? We did number 12. So let's get to 12. 12 will be closer to that calculation, right? So all of that. Okay. 4 times. All of these are 4 times. 3 times. You guys follow me? Right? So this will be 4 times. So all of these will be 4 times for the x coordinates. You see, once you recognize there's some patterns to it, it's actually pretty straightforward, isn't it? From one question to the other, and I especially demonstrated to you how it's been done. Right? I don't want to maintain that, I don't want to leave you guys guessing. How is that done? Why? How come they know they would do it that way? I want to make it completely transparent. Okay, that's how it's been done. Right? So if you understand that process, right? If you understand that process, right? I need to insert a parentheses here, and 3 times of that, right? So the process shows us right? So this is just -3. Oops, what did I do here? 3 times. I forgot that number. What's the cosine 5 pi over 6? -√3 over 2, right? Is that right? Is that right? -√3 over 2. I deleted by accident. Right? So that's how you get your points. That's how you get those points. Okay, I give you all of these points. So then you're going to identify which direction it goes. You're going to identify which direction it goes. Okay. And I think this is going to be a clockwise trajectory. Our time is up. Our time is up. And that's all for parametric. I hope you guys have a good understanding of how parametric graph is done. And in all of these cases, we can convert it to rectangular system, but a rectangular equation. Then this cannot always be done so easily. I want you to understand that, because imagine that the equation xt can get really complicated, y of t can get really complicated, and there are a lot of those situations that you cannot easily convert it, if ever. But you can still produce pictures, and those pictures is going to be very complicated. Some of the pictures you get when you play your computer games, okay, most likely are parametric equations. Imagine your favorite characters jumping from different places, up and down, left and right, sometime on circles. And I think the computer games these days are very sophisticated, right? Parametric equation. Parametric equation. Does that get you interested in? That's how it's been done. That's how it's been done. All right, so without further ado, and I will see you guys tomorrow, and have a great day.
Thank you.
Thank you.